Welcome! Welcome to the Plasma Physics course of TPFL. In the past module, we have deduced the two fluid equations. In the present one, we will deduce the two fluid dispersion relation, that is the relation between the frequency and the wave number of the waves and instability that are described by the two fluid model. In order to do that, the first thing that I will do with you will be to recall the main elements of the linearization and the Fourier mode analysis. Then we will linearize and Fourier transform both Maxwell equation and the two fluid equation. And at that point we will deduce together the two fluid dispersion relation. So let's recall together very briefly the main elements of linearization Fourier mode analysis, something that we have already applied within the kinetic model of plasmas. Our goal is to study the evolution of small amplitude perturbation on top of an equilibrium. Let's take an example, the one of the continuity equation. This says that time derivative of the density is due to the divergence of the flux. In order to study the evolution of small amplitude perturbation on top of the equilibrium, the first thing that we have to do is to separate the equilibrium quantities and the small perturbation. Basically, we will write the density, for example, which is a function of space and time, as the sum of n0, a constant which does not depend on space nor on time, plus a perturbation n1. And as we are dealing with small perturbations, we will assume that n1 is much smaller than n0. Similarly, for the velocity, we will say that this is given by an equilibrium quantity plus the perturbation. Now, if we look at the case of static equilibrium, we will have that this u0 will be equal to 0. And therefore, u will only be given by this small perturbed velocity u1. The second step we do is the one of linearizing the equation, retaining only the leading order terms. The idea is to replace n here with as the sum of n0 and n1, and the u with u0 plus u1. Now, again, in the case of static equilibrium, we can put u0 equal to 0, and the equation we have just written becomes dn0 over dt, by expliciting this time derivative, dn1 over dt, and then we will have, taking u0 equal to 0, the divergence of n0 u1 and the divergence of n1 u1 equal to 0. Now, n0 does not depend on time nor on space, so this is equal to 0. And okay, here we have n1 term, we have n0 u1, and here we have a term that is the product of two quantities that are the perturbed quantity, and therefore which is much smaller than the other two terms that we are retaining. It's quadratic in terms of the perturbed quantities, while these terms are linear in the perturbed quantities. This is therefore, in other terms, a higher order term, and therefore can be neglected. What we come up with is an equation that relates n1, the time derivative of n1, with, taking n0 constant out, n0 times the divergence of u1 equal to 0. At this point we can apply our Fourier analysis. We write in fact that n1, which is a function of space and time, is given by the sum, the integral of the Fourier modes. Therefore will be given by the double integral over all the wave number, all the frequency, of the Fourier transform, which I will denote with tilde of n1, which is a function of the wave number k and the frequency, times the exponential of I k dot r minus omega t. The advantage of doing that is that by Fourier transforming, operators like the nabla operator will become very easy in Fourier space. For example, nabla becomes the operator ik, and while d over dt becomes the minus I omega operator. It implies that by Fourier transforming this equation and looking at the evolution of each Fourier mode, as each Fourier mode is independent from all the others, we get that I omega minus I omega, the d over dt operator, and 1 plus the nabla operator ik dot u1 times n0 has to be equal to 0, which is the equation that relates the Fourier modes of n1 and u1. Okay, we are now ready to linearize and Fourier transform both Maxwell equation and the two-fluid equation. Let's start from Maxwell equation. The equations that are interesting for us are the curl of E equal to minus dB over dt, and curl of B equal to mu 0 j plus 1 over c squared d over dt. From these two equations, taking the curl of the first equation, we have that curl of E is equal to minus d over dt of the curl of B, which is equal to minus d over dt mu 0 j plus 1 over c squared d over dt. And now bringing in the time derivative, we have that this is equal to minus mu 0 dj over dt minus 1 over c squared d over dt. This is the equation that we want to linearize. The first thing we notice is that equilibrium terms in this equation do not play any role. In fact, here we are dealing with spatial or temporal derivative, and therefore the constant uniform value of the equilibrium do not matter. Therefore, only the perturbed terms enter in this equation, and if Fourier transform this equation and we linearize it, we find that minus k cross E1 is equal to mu 0 I omega to d over dt j1 plus omega squared over c squared, which is the d over dt squared E1. Now here we have an ugly beast, the k cross E. Actually, this expression can be simplified by using vector properties that I will remind in a few seconds. K cross E1 is equal to k squared, the modulus of k squared, and then the tensor k divided by k squared minus the unity dyad times E1. Okay, what do I mean with the kk tensor? Component by component, it's the matrix that has of int ij element the value ikj, and which we can write using the x, y, z coordinate as kx, ky, kx, kz, kx, ky squared, and so on. And the unit dyad is the matrix that has the delta Kronecker as the ij element, that is the identity matrix. And now by using these vector properties we can expand this k cross E1, and by multiply times c squared and omega squared, we find c squared k squared omega squared, and then this term here times E1 for the transform, and then here, recalling that epsilon 0 mu 0 is equal to c squared, we have that this can be written as I divided by epsilon square epsilon 0 omega J1 plus T electric field. This quantity here is an adimensionalized number, and we will denote it with n square, and is actually the index of refraction. Okay, what have we found? We have found a relation between the electric field and the current. Somehow we have to work from the fluid side to try to get a relation between the current and the electric field, a second relation, such that by using both equations we will be able to derive the dispersion relation, the relation that will relate omega, the frequency of the waves that or instability that we are analyzing, and their wave number k. Okay, so now our goal is to derive a relation between the plasma current and the electric field by using the fluid equations. We will focus on a relatively simple case of the two-fluid model, the one of the cold plasma. We will therefore neglect all the terms related to finite ion temperature. In other words, we will put the temperature of both electrons and ion equal to 0. This will considerably simplify our study without losing much of the physics that is behind the waves and instability described by the two-fluid model. So we consider the two-fluid equations in the limit of temperature equal to 0. Our goal is to obtain a relation between J1, the plasma current, and the electric field. We expect that this relation will be a linear relation that will pass through sigma, that is the conductivity that in general can be a tensor, that is the mass of the species S times the convective derivative of U. This has to be equal to the electric force plus the Lorentz force. We will neglect the pressure term according to the hypothesis of having the plasma temperature equal to 0. And this equation will be written for the species that are present in our plasma that we will assume to be the ions and the electrons. Well, we will assume that we are considering a static equilibrium, therefore with US 0 equal to 0. That there is no electric field at equilibrium. So basically the plasma will be neutral in steady state. So the species will have the same density, and therefore the equilibrium electric field will be equal to 0. But we will assume nevertheless the presence of a magnetic field, equilibrium magnetic field, that we assume to be uniform. And we will choose our coordinate system in such a way that B becomes aligned to the easy direction. Okay, now we can linearize our equation. This term is a higher order, is second order interperturbation. Only this one, the d over dt remains. Therefore we have ms dus1 over dt is equal to the perturbed part of the forces, which will be given by qs E1 plus qs, and then the Lorentz force. And it's now time to Fourier transform this equation. As usual, the d over dt will become minus omega term, and for the Fourier component of us1 and E1 we will have minus I omega, ms S1 equal to Qs cross B0. From this moment on, as we will be only dealing with the Fourier component of Us and E1, let us drop for simplicity of notation to tilde. Therefore, for the notation, we will, for example, denote E1, the Fourier transform, simply as E1. But we will keep in mind that this is the Fourier transform of E1 and more particularly the K omega mode. Now, since US1 cross B0 can be written component by component as B0 US1 in the y direction EX minus US1 X EY, that this equation can be written as minus I omega, the d over dt term, that will be a diagonal term. Then we can bring the contribution of this term on the left hand side, and what we will find is a minus omega cyclotron for the species S here, and omega is here, 0, 0, dot US1, QSMS, and we leave on the right hand side the E1 term. Well, just as a reminder, the omega S that we have introduced here, the cyclotron frequency, is equal to Qs B0 over the mass. Therefore, we can explicitly writing US1 by inverting this matrix here. US1 will be equal to QSMS times the inverse of this matrix here. And okay, the inverse of the matrix times QSMS can be defined as a tensor μs times E1, where this tensor μs is equal to QSMS. And if you evaluate the inverse of this matrix, things that is a bit boring but is feasible, you get omega minus I omega omega cyclotron square minus omega square, omega cyclotron square divided by omega cyclotron square minus omega 0, and so on. And this tensor, we will call it as mobility tensor, as it will tell us how particles will start to move subject to a certain electric field. Actually, now it's possible to evaluate the perturbed current in a plasma, because it is the perturbed current as the equilibrium flow is equal to 0 will be given by the sum over all species of Qs, the equilibrium density US1. This is the only terms that remains from the linearization of the current, and now we can write the US1 in terms of the mobility tensor and the electric field times E1, and well, this quantity here is actually a tensor sigma E1. We have in fact obtained exactly the relation we were looking for, and sigma, by the way, is the conductivity tensor. We have now all the elements to derive the dispersion relation, that is the function that gives us the relation between the omega and the k's, the frequency and the wave number of the modes that are intrinsically present in the system. What we have to do is in fact to inject the expression of the plasma current that we have derived within the two-fluid model into the Maxwell equations. In fact, by the linearization of the Maxwell equation, we had obtained that minus n square index of refraction times this tensor here, dotted with E1, is equal to the contribution of the plasma current and the electric field. And from the fluid equation we have a relation between J1 and E1. Now we can plug this expression here, and what we obtain is where we have introduced the epsilon tensor, which will take into account the contribution from the conductivity, and this term here. And now we have all the elements to derive, to write down the equation for the dispersion relation of the two fluid model. In fact, the modes that have frequency and wave number such that the determinant of this matrix here, which we can call d of omega k, is equal to 0, so the modes whose frequency and wave number are such that the determinant of this matrix is equal to 0, then these are intrinsically present modes, which can be present in our system and have an E1 different than 0, and solving this equation will actually tell us what is the relation between the frequency and the wave number of these modes. Well, before concluding, let me just write explicitly what is the value of epsilon by introducing the conductivity that we have found. This can be written by introducing three parameters: epsilon 1, epsilon 2, and epsilon 3, where epsilon 1 is defined as 1 plus the sum over all species of the plasma frequency of species S divided by the cyclotron frequency minus omega square. I just remind you that the plasma frequency square of species S is equal to NS0, the equilibrium density, the charge squared, divided by the mass, epsilon 0. Epsilon 2 is equal to minus the sum of the cyclotron frequency over the frequency of the wave, plasma frequency divided by the difference between the cyclotron frequency squared and the frequency of the wave squared. And epsilon 3, finally, will be given by 1 minus the plasma frequency squared divided by omega square. To summarize, in the present module, what we have done is to linearize and Fourier transform Maxwell equation into two fluid equations. In order to come up with a dispersion relation, a relation between the frequency of the wave number of the modes of the waves and instability that are intrinsically present in our system. In the next module, what we will do will be to consider exactly what are the waves and instability present in our system, and we will look at their physical properties.